This video is for educational overview only. Viewers are encouraged to study the topic in detail and continue their academic learning alongside this video. Thanks.
All right, welcome to The Explainer. Today, we're going behind those impressive demos you see online to figure out what it really takes to build an AI agent that can do more than just talk, one that can actually reliably act in the real world.
You know, it's a super common frustration, right? A powerful AI can write a beautiful sonnet, but then it just completely fumbles a simple multi-step task. A prompt that works perfectly one time might fail the next for no obvious reason. It's what engineers call a non-deterministic failure, and that just means you get this unpredictable outcome even when you give it the exact same prompt. So why does this happen? Let's get into it.
Okay, so here's our roadmap. First, we're going to diagnose the problem, the fragile agent. Then we'll get into the fixes, layer by layer, building a better brain and memory, giving it safe hands to work with, teaching it how to fail gracefully, and finally, we'll look at this awesome idea called the Ralph loop that makes these things truly unstoppable. Let's jump in.
All right, first up, the fragile agent. We're talking about the hidden failures of these AI assistants. Because, beyond all the hype, agents in the real world, they're brittle. They have these weird non-deterministic failures where one tiny hiccup can just totally derail an entire multi-step job. So this table really breaks down the main culprits. First, you've got hallucination. That's when the agent just confidently makes stuff up. Then there's context drift. This is a huge one. It's when the agent gets so deep into a long task that it literally forgets the original goal. Some sources actually call this lost in the middle, which is a perfect description. And finally, you have error propagation. This is the snowball effect, where one tiny mistake at step 1 cascades and causes a total system failure by step 5.
Okay, so how on earth do we fix this? Well, we have to start at the core. We need to upgrade the agent's basic ability to think and to remember. So the first big piece of the puzzle is a framework called REACT. That's short for Reason Act. And the idea is actually pretty simple. It teaches the agent to think out loud before it does anything. It generates a little reasoning trace first, and then it acts. This simple back and forth makes a huge difference in its ability to handle unexpected problems and change its plan when things go wrong.
Okay, so a better thinking process is great, but what about memory? The next step is to give the agent a real memory system, and just like ours, it's got different layers. You've got your short-term working memory and semantic memory for rules, but the real game changer here is episodic memory. This is basically a logbook of every time the agent has tried to do a task before. By checking these logs, the agent can actually learn from its past screw-ups and not make the same mistake twice. Pretty cool, right?
All right, so our agent is smarter, it can remember things, but that's all useless if it can't actually do anything. And that's where things get tricky. Giving an AI access to your tools, your files, your command line, that opens up massive security risks. Just one bad line of code could be a disaster.
The way we manage this risk is through something called task decomposition. Instead of just throwing a huge, vague goal at the agent like build a dashboard, you make it break the problem down. First, into a high-level strategic plan, like set up the database and build the front end. And then it breaks those down into tiny, specific, and verifiable steps, what we call atomic tasks. Things like install this specific package. This makes the whole process way more manageable and a heck of a lot safer.
So to actually run those little steps safely, we use what's called an agentic sandbox. You can think of it like a secure digital playground, a totally isolated cloud environment where the AI can execute code, use a terminal, and mess with files without any possible risk to the main system. It can't break out.
Now, it's super important to know that not all sandboxes are created equal. The standard containers you might be familiar with, like Docker, they only give you basic process-level isolation. For real security, especially when you're running untrusted AI-generated code, microVMs are the gold standard. They provide true hardware-level isolation with a custom, super stripped-down operating system, what the slide calls a bespoke kernel. This just means there's a much smaller surface for anything to attack.
And you might think that all this security would make them slow, but the performance is just staggering. These super secure micro-VM environments can spin up in about 150 milliseconds. That's fast enough for real-time interaction. Okay, so we've got a secure sandbox, but things can still go wrong, right? So how does a pro-level agent handle failure?
That brings us to our next section, how to fail gracefully. Because in the real world, things break.
A production-ready agent doesn't just try to avoid errors, it has a really sophisticated, multi-layered game plan for when they inevitably pop up.
And this is way more advanced than just hitting retry. We're talking about smart patterns like circuit breakers. This is where if a tool keeps failing over and over, the agent just temporarily disables it to stop the whole system from crashing. And then there's state checkpointing. This is huge. It means the agent saves its progress after every major step. So if it crashes, no big deal. It can just wake up and pick up right where it left off, instead of having to start the entire job from scratch.
Okay, now we get to what I think is a real paradigm shift. What if, instead of hoping the agent knows when it's done, we could force it to keep working until the job is objectively finished? This leads us to a concept called the Ralph loop. Yeah, it's named after a character from The Simpsons who is, well, very persistent. The core idea is simple but brilliant. You just keep feeding the agent the same prompt over and over. And with each loop, it can see the results of its last attempt in the file system, see the gate history, and try again.
And here's the crucial difference. In a traditional loop, the process stops when the LLM thinks it's done. That's a self-assessment, and it's super unreliable. But with the Ralph loop, the control is external. It only stops when some objective verifiable criteria is met, like, say, all the unit tests pass. Failure is no longer a dead end, it's just more data for the next loop. It literally can't give up.
So why go through all this trouble? Why does all this complex engineering actually matter? Well, it's because we're seeing a fundamental change in what we should expect from AI.
We're basically moving on from answer engines to action engines. For the last few years, we've had chatbots that are really just answer engines. You ask a question, you get a text response. But these new autonomous agents are action engines. They don't just tell you how to fix a bug, they go in and complete the goal themselves.
And this is really the beginning of what you could call the digital employee. We're talking about persistent, proactive agents that will literally become our colleagues. A support agent won't just file a ticket for a bug report. No. It'll clone the repository, write the code to fix the bug, run the test to make sure it works, and then open a pull request with the finished solution. That's a whole different level.
In this whole architectural evolution, it forces us to ask a much bigger question about the future of work. We aren't just building better tools or smarter assistants anymore. We're actually engineering the very first generation of digital colleagues. And that's our explainer for today.